중앙으로 풀출하나요, 마이크를?
그거는 따로 컨트롤.
네, 켰는데 꽂았는데.
Can we start now?
Okay, let's start. Welcome everyone. Thank you for joining us for the first IMAE NAEK workshop. My name is Hyun Kim, a professor in aerospace engineering at Seoul National University. Today we are presenting what's next in aerospace engineering and materials. I'm very pleased to host the first session of this workshop. This workshop is being streamed live on YouTube. So if you have any questions during the session, please leave your questions in the YouTube chat. This workshop is co-organized by National Academy of Engineering of Korea and Indian National Academy of Engineering. Honorable members of two academies and related experts in India as well as in Korea are participating online. Let us now begin with welcome address by the leaders of each academy. First of all, I'd like to introduce the president of NAEK. Professor Oh-kyong will give us welcome address.
Hello, everybody. Good morning in India. Good afternoon in Korea. Although we cannot meet each other in person due to the COVID-19 pandemic situation, I am pleased to talk to Indian and Korean engineers via online workshop. On behalf of the National Academy of Engineering of Korea, I would like to acknowledge Indian National Academy of Engineers' commitment and support to this workshop. In particular, I would like to express special gratitude to Professor Indranil Manna, the president of INAE. I believe that IANE and NAEK are getting closer together our 4 times of workshop. I hope to enhance this relationship and cooperation in various fields. India has become a space powerhouse, developing space technology and continuing to launch satellite, as well as being an economic exchange partner with South Korea. In addition, India is one of the fastest growing countries in the aerospace industry with great support of the government. At present, Korea is growing rapidly in satellite technology, and we are making continuous effort to obtain our own technology in aerospace industries, such as Korean combat aircraft and propulsion rocket in the near future. In this sense, Korea and India will be able to cooperate in various areas. For example, both countries are using 3D printing for aerospace parts manufacturing. Korea produces aviation parts in 3D printing, and India also uses 3D printing technology for parts for satellite and aircraft. Reflecting this trend, today's workshop will be discussed what's next in aerospace engineering and materials. While finding common ground in aerospace engineering between two countries, I hope we can expand our cooperation to Internet of Things, big data, and artificial intelligence necessary for aerospace industry. In order for two academies to achieve this goal, I hope this forum will foster live discussions on cooperation between Korea and India that will benefit to all our nations. Thank you very much.
Thank you, President Kwon. Next, I'd like to invite the President of INAE. Please welcome Professor Indranil Manna.
Good afternoon, Professor Oh-kyong, President NAEK, Professor H.J. Kim, Professor Yung-Gyo Kim, the session chair for today, and colleagues from Korean NAEK, namely Drs. Lee, Dr. Shin, Dr. KARI, Dr. An, Dr. Kim, and Dr. Lee. I think this is the order in which they will be speaking today and tomorrow. Good morning to my colleagues from India, in particular from INAE. Professor Bhanushankar Rao will be the chair tomorrow. Professor Mittal, Professor Banerjee, Dr. Somanath, Professor Basu, Professor Joshi, and Professor Suhas. I would also like to welcome all the participants who are watching this program live, either from India or Korea, or anywhere from the rest of the world. I'm very pleased to welcome you all to this fourth workshop of INAE and NAEK, the two National Academies of Engineering in India and Korea. Let me remind us all that the journey started in 2017 with the first workshop in Bangalore, the second one in Changwon, Korea. I had the privilege of leading the team to that particular occasion. The third workshop was held in 2019 in Hyderabad. Last year, we couldn't hold the workshop because of the pandemic, but I'm very glad that we are back on action, and this is the fourth workshop on the future of aerospace engineering and high temperature materials, in particularly through the route of additive manufacturing. Like Professor KARI mentioned, that both Korea and India have several areas of ambition in common in the technological space. But before we come to engineering and technology, it would be very pertinent to remind ourselves the very many common interests and historical facts between Korea and India. I think the foremost thing would be that we are the two nations, probably a unique coincidence that we share the Independence Day, 15th August, though Korea got its independence 2 years ahead of India. Buddhism is a very major link between India and Korea, and it's very interesting also for all Indians to know that the Koreans believe that their first king, Kim Su-ro, in 48 AD, married a woman from Ayodhya. We are not sure whether this is the present Ayodhya or the Ayodhya of the Ramayana era, but this lady, Sri Ratna, was the wife of the first king, and as the first queen, the Koreans believe that this queen, Hyoun, actually brings the closest relationship possible between Indians and Koreans, because almost 1/4 of the population who bear the family name Kim probably carries some link with this woman from India. We were fortunate during our visit to Korea to visit Kim-hae, which probably also means Gaya in Busan, the kingdom. And we were very pleased to see the historical relics there. And my little homework also told me that there's another very interesting common fact between India and Korea, and that is the board game of Yat, which in India is called Ludo. But from history to come to the present day, I would like to share with my colleagues from Korea that INAE was founded on 20th of April 1987. This is the premier engineering academy of the country with 869 fellows, 87 foreign fellows, and 126 young associates. We cater to our population interested in engineering, starting from the college days all the way to very senior level. So we have Innovative Student Project Award for foreigners, for our young engineers who are in engineering education. We have awards for young engineers at the below the 35-year age level. We have several fellowships and awards to promote engineering, even among the women and those who are entrepreneurs. Apart from electing fellows, we also give awards to the illustrious engineers and technologists of the country. We have 4 very major calendar events, starting with the National Frontiers of Engineering, then Youth Conclave, Engineering Conclave, and finally the annual convention at the end of the year. INE runs certain forum to discuss topical engineering aspects like energy, technology development, disaster mitigation, and so on. INE publishes an international journal called Transactions of INE and an e-newsletter. We also care for the society by pursuing projects in terms of frugal innovation, and on the other hand, at the topmost technological directions like regional transport aircraft or prevention of national disruptions. Like NAEK, INE also is a very active member of KATES, the International Congress. We would like to take our collaboration and cooperation that the President NAEK mentioned at the beginning to the next level. So we have been running this workshop, and I must mention that we do have exchange programs or cooperation with the engineering academies in USA, in Germany, in France, and several other countries. But the interaction with Korea is not only very active, but probably the most regular. So I certainly, on behalf of INE, would like to thank the Korean Academy and its president for pursuing the collaboration so strongly. But let's take it to the next level. President NAEK mentioned about certain technological priorities of Korea. Similarly, in India, we are very much devoted to our space program. We are in the process of developing a scheme to develop the regional transport aircraft. We all know that both Korea and India occupy very important space in the field of steel. And we were privileged to see the POSTEC during our visit. I'm aware that Korea has made tremendous progress in electronics and electronic materials, in automobile manufacturing and components. And today we also have certain common interest in artificial intelligence and machine learning. So using this platform, I would like to propose that let us try to create certain INAE, NAEK engineering exchange fellowship, whereby we can sponsor a limited number of young and established professionals to visit Korea, and similarly to invite such professionals from Korea to India, and the respective academies can fund their international travel, whereas the local academy can take care of the expenditures for hosting them in the respective countries. But this is for us to take forward in future, whether we can make it happen. Of course, we need the government's permission for funding and other clearances. But I thought it is time that the 2 technological giants and the 2 largest economies of the world should come together in a more interactive manner and take our collaboration further ahead. So with this, I would like to conclude, and I would like to wish this workshop a grand success. I thank all the speakers who have kindly agreed to speak in this particular workshop, and I'm sure through this interaction, we stand to gain a lot of new knowledge. Thank you very much. Jai Hind.
Thank you, President Manna. The first session today is about aerospace engineering systems and aerodynamics. The first speech will be given by Dr. Yung-Gyo. He is the director of Aeronautics Technology Research Division at Korea Aerospace Research Institute, or KARI. He'll give us a presentation on Korean solar-powered stratospheric UAV development. Just a reminder, please feel free to leave your comments or questions in the YouTube chat during the presentation. We'll have time to answer questions at the end of this session. Thanks.
Okay. Hello, my name is Yung-Gyo Lee, and very nice to meet you. I am working in Korea Aerospace Research Institute. And today I will give you the presentation about Korean solar-powered stratospheric UAV development. Then why we use the solar power for HAIL UAV? For long endurance and for eternal flight with regenerative solar energy is essential. Also, at high altitude, electric motor has no performance degrade. So we use electrically powered system like battery, fuel cell, solar cell. Our UAV will be used for telecommunication in the stratosphere, and also weather observation, also disaster, and border watch. Now, in other country, EADS developed the 제4회. It has flown 25 days at Arizona in 2018. So it is designed for internet service with laser communication. Its wingspan is 25 meters. The solar cell and a lithium-ion battery is used. Also, HAPSMobile designed the sun glider. The purpose is also the telecommunication. And last year, it has succeeded in telecommunication at stratosphere. Its wingspan is 78 meters, and the solar cell and lithium-ion battery is used for power system. Now, this is KARI's EAV program. From EAV 1 to 2H and EAV 3, we mainly use a few battery and a solar cell. And sometimes we have used a fuel cell, but now we are using solar cell and lithium-ion battery. The span is from 2.4 meter to 20 meter. The maximum weight from 7 kilometer to 66 kilogram to 66 kilogram. The performance is advanced from 2010 to current. So now I will explain you one by one. This is EAV1. The power source is a fuel cell. The purpose is the technology identification for aircraft electric propulsion. So we have modified this from existing platform and from lithium-ion cell to fuel cell. So wingspan is 2.4 meter and the weight is 7 kilometer. It's all composite UAV. EAVs are all composite UAVs. The duration improved from 2 hours when it used a battery to 4.5 hours when it used a fuel cell. The first flight was done in 2010. This is a fuel cell and also a hydrogen generator. Adding water to boron compound, it will generate hydrogen. So we use bungee takeoff like this to reduce the runway usage. So EAV, all the EAV doesn't have any landing gear, so it just uses the wire skid under the fuselage and under the wing. No. And this is EAV2. The power source is a solar cell, fuel cell, and a lithium-ion battery. The purpose is, this is a concept demonstrator of a hybrid power system. The wingspan is 7 meters, weight 18 kilometers, and its duration is 22 hours. The first flight was 2011, so this is typo. And in 2012, it has flown 22 hours and 13 minutes. EAV2 also doesn't have any landing gear, so it will land with the wire skid under its wing. So the speed is so slow, so no damage it will have when it lands like this. This is wire skid. So it has a folding prop and also a hydrogen generator, fuel cell stack, and also a fuel tank. So it uses during the flight. The solar cell is using for daytime, and the fuel cell is used for nighttime, and the battery is used for a high power peak cut or stabilize the power system. So solar cell, fuel cell, and battery is used for propulsion system and also the power system. Ground tests consist of these things: probe wind tunnel test, the solar cells on the wing deflection test, and the power system, also 24 hours of integration test. Now this is a 2H program. H means high altitude. Power source is a solar cell and the lithium-ion battery. This is a concept demonstrator of a HAIL system. Wingspan 11 meters, weight 20 kilograms, duration is 25 hours. AV2H is a single prop version, and the 2H Plus is a twin prop version. The first flight was 2012, and it has flown 25 hours in 2013. Other EAV used a monocrystalline silicon solar cell, but in this version, it used the amorphous solar cell on Mylar windskin. It has a low drag aerodynamic design, and also ultralight structures was applied. Also 18650 battery is used. The energy density is about 210. Ground tests are like this. Structural load test was done for the wing, and also air data system calibration was done in the wind tunnel. And the propeller wind tunnel test was done, and the 24 hours integration test was also performed. It has used the omnidirectional combined antennas. Now this is EAV2H flight to 10 kilometer altitude. So it reached 10 kilometer in 2014, and it experienced a jet stream over 9 kilometers in Korea. This is EAV3 concept demonstrator. So we have the camera on board, and some pictures was recorded on board. Okay, next. Now, this is the EAV3 program. EAV3 uses solar cell and also lithium-ion battery. The solar cell is a single monocrystalline silicon solar cell. The purpose is a stratospheric operation, and we have constructed 3 EAV3. This is the spec of number 3. Wingspan 20 meter, weight 66 kilometer, max altitude 22 kilometer. The speed from 25 to 43 kph-EAS. The duration was of 53 hours last year. The EAV30102 has, this is the EAV30102. The EAV303 has a more solar cell, also the bigger fuselage. Now this is a this is a power propulsion system. EAV3 has used a single crystal solar cell. It's a 930 panels of 30 panels. Also, we have 8 packs of battery pack. That's a 7.2 kilowatt hour. We have applied 2 types of solar cell. One is a lithium-ion solar cell made by Amprius of USA. It has about 390 watt-hour per kilogram of energy density. And the other version used lithium sulfur solar cell made by LG Chem of Korea. It has an energy density of more than 400. And through the component environmental test and also BLDC motor development, and also high altitude propeller design, the EAV3 has flown to 22 kilometer height. The test condition was negative 30 degrees of Celsius, and the pressure is 1/20th of sea level atmosphere. The solar cell panel is tested in the environmental chamber. Also, battery cell and the pack inflates and deflates during the flight. So we have, they has gone through the pressure testing in the pressure chamber. This is a battery pack low temperature test, motor and control board test, and avionics environmental test. Also, the motor driver was tested in the dry ice box to get negative 70 degrees of Celsius. And this is a floater model of the EAV3 structure. Horizontal axis means wing loading, weight divided by wing area. And the vertical axis is total weight. So EAV2 started in this conventional aircraft area. Now through the EAV2H, EAV3, we have achieved ultra-light structures. Our all-composite aircraft used T800 carbon fiber, and number 3 used the T1000 carbon fiber. Okay, we also went through the flutter simulation. Also, we did a steady load test, propeller wind tunnel test, and also double redundancy air data system. We have 2 AOA sensors and 2 AOS sensors and 2 pitot-static systems. And we have gone through the durability test. In the stratosphere, temperature negative 70 degree, pressure 0.05 bar, and density is 1/15th of mean sea level value. So in the lower part of a stratosphere, the temperature grows up when it climbs up. In last year, August, in KARI Gohung Aviation Test Center, it has flown 2 complete day and night cycle. Max and mean altitude is 18 kilometers during day and 5 kilometers during night. So environmental condition was 6.5 kilopascal. So this is blue line means the outside air temperature. So higher than 16 kilometers, the temperature went up because this is ozone layer, and it means we are in the stratosphere. Now let's enjoy 2 minutes of video. This is flight testing. This is our Hyoun Aviation Center. Tracking antenna for C-band communication. Altitude 1.5 kilometers. From onboard the camera. Okay, the ground control system is like this. The altitude is 18.5 kilometers. We have reached it. Also, propulsion system monitor, the onboard camera, and the Seoul Island taken from 18.5 kilometer altitude. Now, the achievements from EAV1 to EAV3, the endurance from 4.5 hours to 53 hours, and also the altitude from sea level to 22 kilometers last year. So we have made many achievements. Now, EAV future plan. Next step would be year 22 to 25 is planned. The target is a 1 month continuous flight over 12 kilometer altitude, totally in stratosphere. The wingspan is 30 meter. The weight should be under 150 kilogram. The payload is enlarged. It's a 20 kilometer. It's a kind of a very big payload for this type of aircraft. And we will apply satellite communication for wider area operation. To do that, we have to minimize power consumption, and also weight reduction is very critical. So structural weight reduction will be, it should be under 50 kilometer with a 30 meter wingspan. To do that, new structural concept should be applied, and also T800, T1000, or maybe hopefully T1200 carbon fiber we will need. So I hope we will succeed our next goal. So thank you for hearing.
Hey, thank you, Dr. Lee.
You're welcome.
Now let's move to the next speech by Professor Sanjay Mittal. He is with Department of Aerospace Engineering at Indian Institute of Technology, Kanpur. He's going to talk about air intakes of high-speed aircrafts and reusable launch vehicles. Okay, the stage is yours.
Thank you very much, Professor Kim. It's really a pleasure to be here in this very nice event. I'm going to talk a little bit about some of the work that my students and we have been doing here at the Indian Institute of Technology, Kanpur. This picture is from one of our very iconic buildings. It's the Central Library. And in fact, it was also released as a postal stamp some time ago. So as you may be aware that India has done quite well in at least two domains, the nuclear and space. And in terms of, as was also mentioned in the opening remarks by the Honorable President, that we launch satellites for other countries as a commercial venture. So it's a fairly successful program. And one of the key things is the low cost. That would be an advantage. So there's always this tussle between rockets versus air-breathing engines. So rockets are a little bit easier to put together. But when you talk about air-breathing engines, then you have to collect air, undergo combustion, and then perhaps also reuse them. So just to give you a number, air-breathing engines overall can be about 80% lighter, and therefore they offer a very economic advantage over the rockets. So India has a very ambitious program to go ahead with a two-stage to orbit system, wherein you take off like a space shuttle, and then there are these two stages in it. At some point, you jettison one of the stages, and it comes back and lands as an aircraft. And the other part, it actually goes ahead, and then you can deploy a satellite. And once that is done, that also is retrieved, and the system is completely usable. So one of the challenges in this kind of a system is to use a scramjet. That's the air-breathing propulsion. So you essentially collect very rarefied air in the outer atmosphere, and then use it to propel your aircraft. Unlike a rocket, which would have to carry hydrogen and oxygen from Earth, and therefore it would be very heavy and expensive. So the bulk of this talk is about air intakes, okay, which is an essential part of a scramjet engine or a ramjet engine. So just to put things in perspective, I have shown here a beautiful picture of Concorde, just for the viewers who may not be familiar what an air intake is. So there are these Olympus engines in the Concorde, and they are fed through these 4 pods. These are the air intakes. So they are passive devices wherein they just collect the air from the atmosphere, and they just transmit that to the engine. Okay, so it seems very simple. And here is a close-up view of these 2 intake ducts. So the challenge for an air intake is the following. First of all, I have an engine at the downstream end of these intakes. So I must have almost a uniform flow at the engine. Otherwise, there could be heavy distortion of flow, and that would lead to loss of efficiency. The second one is that I must slow down the air so that I can have combustion inside my engine. As you are aware, if my aircraft is traveling at a very high speed, and I allow the air to get into the combustion chamber at that high speed and put fuel in it, then I will not be able to stabilize the flame. In fact, the flame will blow out, just like a candle will blow out if you put the candle on top of a truck and speed your truck. Okay, so essentially you have to slow down the flow that comes into the combustion chamber so that you can have efficient combustion. So that's the job of an intake. Again, 2 jobs. One is to supply air of enough mass flow rate at low speed, and the other is flow uniformity at the engine. So here is a schematic of what a typical reusable launch vehicle which uses air-breathing propulsion would look like. So on the vehicle at the belly, there would be this engine, so it's integrated with the aircraft. And through a set of shocks, which are shown over here through this schematic, the flow slows down, and then you probably have another set of shocks. You put in the fuel, and because here the speed of the flow is relatively low, so you can have combustion, then you expand it, and that's how you produce power. So what I want to talk about is just this part of the aircraft, the air intake, where there is really no combustion. So you just want to make sure that the design is good enough, that you get adequate mass flow rate. And because there is high pressure inside the combustion chamber, and there is low static pressure in the atmosphere, so it provides a nice balance between low pressure at the inlet and a high back pressure at the engine face. Okay? If you are not able to account for that, then essentially this whole content is going to move upstream and you are going to have something called the surge or an unstart of an intake. So there are several types of air intakes in aircraft engines, and I have given you some examples. So there could be an external compression intake, wherein the shock systems are completely outside the engine and they slow down the flow. Or you could have a completely internal compression system wherein all the shock structures are inside the intake. And of course, the most likely one, which is going to be efficient at these Mach numbers, high Mach numbers, is the mixed compression, wherein you would have a mix of both external and internal compression. So I'm going to show you some results for our analysis of a mixed compression intake, which offers a very good potential for these flight vehicles. Before I do that, I just wanted to show you some ideas of operation of these intakes. So here is the schematic. So there is a high speed flow coming in from left to right. And this is the center body of the engine, shown in purple color. So you have these shock systems where the flow slows down. This region we call as the throat because this is the minimum area region of this device. So that's called the throat, as the name suggests. We would typically have a normal shock somewhere in this system, and we would like it to be as weak as possible to reduce the losses. As many of you may be aware, you can have losses across a shock, and the higher the Mach number across the shock, the Mach number drop, the larger will be your losses. So you want the upstream Mach number to be as small as possible for the shock to be weak. The critical would be the design situation. So here you would put the shock right at the throat. So you would design the trajectory of your aircraft and the whole system so that the shock resides at the throat. Here the Mach number is very close to 1, and therefore this would be the most efficient system. But it is critical in the sense that it is neutrally stable. If you push the shock, if there's a small disturbance, then actually, I'm sorry, it's not neutrally stable, it is unstable. So if there's a small disturbance that pushes the shock upstream, then actually one can show that the shock will keep going upstream and eventually the engine will unstart. Okay, and there would be no mass flow rate through the engine, the combustion chamber would not get any fuel, and then you would have a flame out. So it would be as if somehow the vehicle loses power and then it would just drop down like a stone. So you don't want this operation. You would like to keep a small gap between the design and the actual operation, and therefore you usually operate in a supercritical situation wherein the shock lies a little bit downstream of the throat. Now here the efficiency is not as high as in the critical regime, but then you have some margin for the instability to be controlled. So if the shock moves a little bit upstream, you are still okay because it has not crossed the throat. The real problem would be the subcritical operation. If somehow the shock goes upstream of the throat, that typically would be a disaster, and you do not want that. So it would be useful to, before you make any hardware, to maybe do some simulations and figure out what is the zone of operation in the Mach number, altitude, back pressure, parameter space of where you can operate your vehicle. It could be a launch vehicle, it could be an aircraft, it could be a missile, any flying device. So here's a schematic of, I've taken from the internet of what typically happens. So just to give you a perspective, flow is coming from left to right. This is the center body. You get a system of shocks. So the flow slows down. And when it has slowed down enough, then you can inject fuel and you can have combustion, and the high-speed gases can be expanded through the nozzle, and that would give you thrust. So typically when you want, if you're a pilot and you want more power or more thrust, you step on the throttle and you inject more fuel. So when you inject more fuel, you would like to have more air, and that would create more pressure inside your combustion chamber. So you would like this air intake to operate at a high back pressure ratio, in the sense of the pressure ratio between the inlet and the back pressure. Okay, so we chose, being a university, we chose a geometry that is available in open literature. So this was tested long time ago by NASA. So this is a double ramp intake, 7-degree ramp followed by a 14-degree ramp. This is the cowl, and this is the ramp, and you have flow from left to right. So the first calculation was done by assuming there is no viscosity. So we use Euler equations. So some finite element calculations were carried out, and we obtained a flow. And then we carried out viscous calculations by turning on the viscosity. And what was found is that the viscous effects really cause a problem in this flow. There is massive separation because of this shock. So the boundary layer separates. And the color coding here is red denotes high Mach number. So that's 3, the inlet Mach number. And blue is close to 0. And then there are shades in between. So you get massive flow separation. And you get very little mass flow rate through the engine, even when the outflow is supersonic. We have not even applied a back pressure. So there is no combustion right now. And still, this is not performing well. So one way to resolve this problem is to use boundary layer control. And typically what is done is that there are some holes in the ramp and the cowl. It's a porous material. And you remove some air from this and perhaps use it for air conditioning or cooling. Okay? And by doing that boundary layer control, you can actually prevent the flow separation. So we did some analysis for that. We tried to figure out where the shocks are formed, how they separate the boundary layer. And then we came up with these regions of the bleed, boundary layer bleed, region 1, 2, 3, 4. And then we experimented with where the bleed would be more effective. So I'm not going to go through those details here, but I want to show you some instabilities, which actually are very interesting. And in fact, they should be avoided in a real system. So after the bleed is implemented, you can see that the intake now starts. So this is with the 6% bleed. The boundary layer is now very nicely attached. And in fact, it looks as if this is an Euler flow with almost no viscosity. But in fact, there is, because I'm showing you here the vorticity in the right. So there is a boundary layer, but it is very well behaved. And the flow is perfect. So this is a good candidate. And now we can start increasing the back pressure and then see how this intake reacts to that. So here is a typical plot that would be useful for somebody who wants to design intakes. So the x-axis is the back pressure ratio. So if there is no, if there is no flow, then the pressure ratio is 1. The back pressure is same as the inlet pressure. And then slowly you want to increase the back pressure because that's going to be equal to the combustion pressure. And you want your intake to operate at as high a back pressure as possible, okay, and at high efficiency. This is the mass flow rate that the intake would permit. So these are in some non-dimensional form. And what I want to show you here is that if you use, let's say, 6% bleed, then your intake performs well up to a certain pressure ratio. And then beyond that pressure ratio, very quickly the performance deteriorates. In fact, you can see there's almost a jump wherein the intake does not admit this high mass flow rate. So for the combustion to take place, the engine has been designed to deliver this kind of a mass flow rate. But if you increase the back pressure by somehow increasing on the throttle, you get this high a back pressure ratio, and therefore the mass flow rate reduces. And in fact, your engine will not be able to generate thrust. So this is a big no. So you want to analyze how well your intake is performing for different bleed ratios, for example, and other conditions. So if you're willing to do a very high bleed, let's say a 27% bleed, then your engine would actually do quite well at very high back pressure ratios. But then if you go beyond a certain number, again, the mass flow rate is extremely poor. So I want to show you one case which is on the verge of being unstable. And you can see here it is very close to the critical operation. So that's the throat of the engine. There's a back pressure. As you will notice, we are applying bleed, so there are very small Mach waves on the ramps. But more or less, the flow upstream of the throat is steady. But then there's major flow separation and unsteady activity downstream. And you can see these shocks which are kind of dancing back and forth. But it's still okay. This is a reasonable situation, and the pilot can still use the aircraft. If you increase the back pressure even further, you can get an instability, which I'll show you in a moment, which are typically called buzz. So just to demonstrate to you what a buzz looks like, I'll create a sound. It's almost like a honeybee creating a buzz, bzzz, something like this. Okay, so it's the shocks traveling back and forth. And essentially what happens, the whole duct of the air intake acts like an organ pipe, and you can get standing waves which lead to this acoustic response. So we have two kinds of buzz, a little buzz and a big buzz, and both of them are driven by superharmonics of these modes that I have shown here in the pipe. So here is an example of a little buzz. Okay, notice we started off with a low back pressure ratio, and then as soon as the back pressure ratio was increased, this mass flow rate with time, you can see a very periodic type of a response. So you get a high mass flow rate, then it becomes low, then it rises again. So it's a very periodic activity. And that's because these shocks are going back and forth. I'm afraid I do not have time to explain the physics of why this happens, but this is called a buzz instability. And what it can do is, it can actually resonate with the structural aspects of your engine. And then if the two match, then there can be a complete disaster. Also, as you can imagine, because the mass flow rate is time varying in this manner, the thrust will also time vary, and your aircraft would get a periodic thrust, not a steady thrust. So it has a very predictable frequency. So that's the non-dimensional frequency. I'll show you an example of an even more catastrophic buzz, which is called the big buzz. So here the shock systems are extremely strong, as you can see. And there is even more massive flow separation. So these shocks are going back and forth. So the engine fills up, then it empties again. And in fact, if you look at the mass flow rate, then you can in fact have a negative mass flow rate at the throat, wherein part of the cycle, the flow goes downstream, and in another part, it actually spills over and goes out of the engine. So this is a big no. You do not want to use this in a real engine. That's bad news. This one has a fairly large frequency, okay? And this could be of the order of several kilohertz. You could also have a situation wherein you could have, a big buzz and a little buzz following each other. So this is an example of a little buzz followed by big buzz. So initially you would have a low frequency response, and then eventually you would get a high frequency response of the mass flow rate through the engine and the related forces. I have a few more minutes left, so I'll just very quickly show you some other intakes that we are doing, maybe a couple of minutes. So there are other intakes in aircrafts that are used, for example, the wide duct intakes. So you could have a situation where you have one engine and it is being supplied by two air intakes, much like our nose, where we have two nostrils supplying one air column. Or of course, you could have two curved ducts supplying one engine each. So simulating air through these curved ducts is yet another challenge of how you supply the air to the engines efficiently. So we chose this model problem of two ducts which are joined together at the merger section. And then we are going to look at what is the effect of the pressure ratio. So the engine is located at the downstream and the air comes from the left. And we are interested in what happens at different side slip angles when the air is not coming actually to the aircraft is side slipping, and of course different pressure ratios. So these are the boundary conditions that are used for the simulations, an example of a mesh. And these are the kind of pictures that one can generate through CFD. and compare them with, in fact, pictures that one can get from experiments. So this is completely a numerical picture of a density gradient. And those of you who are experimentalists will appreciate that if you look at this picture, it looks as if it is straight away from experiments. So very complex flows of interactions of shock waves and expansion fan and the related boundary layers. So one can get a picture of the back pressure ratio on the x-axis, the side slip angle on the y-axis, and then try to figure out what are the different flow regimes that one can get. So just to cut a long story short, you can have, when at low back pressure ratios, this shock train, they become stronger as you increase the back pressure ratio. Then you can get this lambda shock, followed by the bow shock standing outside the inlet. And then you can get a region of separation. And this would lead to a buzz instability, wherein flow would come in through one of the ducts and actually leave through the other duct. And finally, you could get an unstart. So again, you don't want to be in this regime. And just to wrap up, this is the mass flow rate that you would get with respect to pressure ratios. And just to complete the show, these are some flow pictures for the different regimes. And I would like to particularly show you a case of a buzz. So here, the side slip angle is 5 degrees. So the aircraft is actually not, it's actually at a side slip angle. So it's getting more mass flow rate through the lower limb as opposed to the upper limb. And here is a close-up picture of that situation. And as you will notice, flow comes in through the lower limb, and in fact, it curls around and leaves through the outer limb. So in fact, one of the limbs shows a negative mass flow rate, while the other one shows a positive mass flow rate, and you get very little flow through the air intake. And this is not recommended for a real operation, but as a design engineer, you would like to know how the intake behaves so that you can avoid these uncertainties even in the testing phase. So I would like to stop here. Thank you very much for your kind attention and for giving me this opportunity to interact. Thank you.
Okay, thank you, Professor Mittal. Our next speaker is Professor Sang-Jun Shin from Department of Aerospace Engineering at Seoul National University. He's going to talk about urban air mobility and research, related issues in Korea.
Can you hear me clearly? All right. Okay. I'm currently out of my office, so this place may be a little bit noisy and a little bit dark. I need to apply for that. And okay, before I go on to my presentation, I'd like to thank my colleagues to prepare for this presentation. Let me begin. Next slide, please. Is it okay? I'm sorry. I'm not sure what's happening. Can I just no, it's not. Oh, there we go. I think I got to come back soon with my presentation file here. It's not working. I need to apply for that. I'll be back as soon as possible. I'm sorry.
Dr. Lee, can you answer a question while Professor Shin is getting ready? There is one question for your presentation.
Yes.
Okay, thanks. So let's see. The question was, if there is an optimum height for maximum endurance of your UAV?
No, actually, in high altitude, the density gets lower, then it consume more energy. So the lower the altitude, the less energy it will use. So there's no optimum height.
Okay, thanks. Then there was a comment about collaboration between India and Korea. So there was a comment about one of Korean satellites, KitSat-3, was launched on the Indian PSLV launcher. So he reminded us for further collaboration between two countries. Thanks. Okay, Professor Shin seems to be getting almost ready. So I'll have him take the podium again.
Okay, I'm back. I'm sorry for this delay. Now, I like to make it. The presentation title will be about urban air mobility and the current activities in Korea. And this is the brief outline, my presentation this afternoon. And I believe almost everyone, you guys will be very familiar with this word, UAM, on urban air mobility. It is mostly like a new airplane or aircraft, but it also involves many other activities like the vertiport and the controls and the regulations and the laws and the others. And all these results, all these actions is due to the modern urbanization in the global scale. And the transportation becomes a big burden in almost every big urban cities. And it is quite natural to produce and develop new ways of transportation. And I also believe everyone is now very familiar with this electrically powered, the vertically takeoff and landing aircraft, which is shortly called eVTOL. And as you see here, many advanced technologies are integrated in one vehicle. But and it looks quite easy and quite straightforward. But as many new aircraft was to be built, it will involve many different and many difficult activities. I'd like to show some of them in the coming slides. By the way, by using such a new transportation ways, a new market or new paradigms will be open, and many economical organizations will predict such market will grow quite in a big scale, which is shown here. Now I'd like to introduce some activities currently initiated in Korea. By the way, people in Korea started the business about the eVTOL and UAM in Korea. They started the business about the UTM, which is the UAS, unmanned air system, the transportation or traffic management. And it's been a few years for them to start a new research plans and project about this UTM, and by now they made a significant result in developing and establishing the result of it. And this is the picture of the new site to be built in Korea, mostly in the new rural areas, to test and regulate the small size, the unmanned air vehicle, which is in relation to all the regulations and all the certifications under the government action of Korea. Now there are a few activities which is directly related to the UAM or eVTOL in Korea. They are either the government sectors or the private sectors. As a matter of fact, it is quite famous and quite prevalent about this new transportation in Korea, but the government effort or government the financial plan is not clearly established yet. But beyond that, difficulty is one significant project under the Korean government support has been examined, which is called the optionally piloted the personal air vehicle. Here, the optional pilot means either the piloted or remotely piloted. And this slide shows that effort, and they already started the small scale, the flight test, and I believe they will soon build the full scale aircraft and the flight test. The size of the aircraft is about 1,433 pounds, which is a little bit big. And its range is about 60 kilometers. And here are the two other efforts which are done by the industry sectors. One is by the Hyundai Motor Group, which is famous for the automobile industry, but they somehow found a new interest in this new area, and they started building the new aircraft and new vehicles, both in Korea and the United States. And the conceptual vehicle shown below in the slides, which is SA1, has been built in the United States and probably been going through the regulation procedures in the United States. The other industrial efforts done in Korea by the Hanwha Systems Incorporated, and the way this industry has been doing is quite similar to the way that that has been done by the Hyundai Motor Group. The Hanwha System built a common invested corporation in the United States, and they have been collaborating with that international industry in the States, and they've been building this new prototype called Butterfly. And their plan is to complete it within the next few years, and as well as the flight vehicle development, they will do some efforts on the regulations too. Well, those are the examples which were been going on in the government sectors and industrial sectors in Korea. But even though it is quite small and quite in the beginning, but in the academia, like Seoul National University, they started a new research project which is related to the UAM. Again, the first one is the same UTM, the unmanned air system, the traffic management research program, which is done with the government of the transportation in Korea, and various activities were planned and done under that research program. The other one is a new research center that has been recently approved by the government of the science and ICT in Korea, which is mostly focused on the flight vehicle. And 6 universities will be joining in this program for 7-year research program. And there also exist international collaborations with Boeing, Airbus, and NASA Ames. Under that program, mostly the aspects within the vehicle technologies will be focused on, and the 7-year research period will be separated by phase 1 and 2. During the phase 1, the basic research efforts will be attempted, and during phase 2, those various aspects will be collaborated and will be integrated, and to focus on a final prototype, which will be designed by this the artificial intelligence based the simulation program. And under that phase 1 and phase 2 program, the many different disciplines will be expanded and will be integrated in the final result, such as the preliminary design and all those aerodynamic, structural, vibration, acoustics, and the flight condition controls. And these efforts will be collected and collaborated with the existing UTM activities going on in Korea. And as you see, the eVTOL or UAM aircraft vehicle will be similar to the rotorcraft, the vertical takeoff and landing, and many existing the technologies related to the rotorcraft in Korea will be naturally and automatically merged into this effort. And this is the final construction of the ideal and imaginary the flight vehicle, which will be done by the integration of all those efforts inside the research effort. Now, this is the small conclusion of my presentation this afternoon. Even though the aircraft and the flight vehicle is an integration of many different disciplines, but as well as this the flight vehicles, many other research efforts will be required, such as the infrastructure, regulation, and operation. And within the research center and within Korea, there are many activities and many research plans will be done in Korea, which is in relation with the UAM and eVTOL. Thank you for your kind attention. Thank you.
Okay, thank you, Professor Shin. We'll go ahead and take some time for questions, and we are receiving questions via YouTube chat. So if you have any questions, please feel free to type any comments or questions. Okay, Dr. Shin, I have a question. So people ask me like when the UAMs will be reality in Korea, and what about the regulations and like safety? So people see accidents by helicopters and things like that all the time. So they are wondering if enough redundancy can be made on a small platform to ensure safety of passengers and people down on the ground. What's your opinion about that?
Right. Well, I believe there are two things. The period that many different companies inside Korea and throughout the world, they have different points or different time locations in which they will complete their development. Like the Joby Aviation, which is one of the very finest companies in the United States, they think they will be done, that they will complete their flight vehicle by 2024 or 25. Hyundai company, Hyundai Motor Group, they think they will be done it by 2029. Then there is a little bit variations about this the flight vehicle development. The second thing is the regulation. Well, regulation is well, for example, it has been going on by either the FAA in the United States and EASA in Europe, and similar efforts has been done by the Korean Ministry of Transportation and Construction. Well, it depends on each other country's situation, but they think they will be able to build, construct all the required regulations within 5 years. So by the year of 2029 and 30, well, but there's still people have many concerns about the safety, as well as all those acoustic noise and concerns. So I personally believe it will take another few years to build all those the beliefs and the satisfaction. So I think by the year of 2035, I believe I think we need to take a few years to establish all those the concerns and all those the technical breakthroughs. So I think the final answer is about the year of 2035. So it'll be a little bit long from now.
Okay, thanks. If there's no question from the chat window, let me ask you another quick question. So I think the noise that you just mentioned is one of the severe obstacles toward the utilization of UAMs. How much reduction of the noise can be made by optimum design, in your opinion?
Well, there's no regulation. There's no regulations from the offshores like FAA or EASA, but naturally the companies and the organizations who are building the vehicles right now, they are establishing their own targets, like 6 dB reduction beyond the level of the rotorcraft, the same size rotorcraft. 6 dB is quite big, quite a big reduction. But the question is, how can you make that? How can you ensure that reduction? And because of that, many interesting ideas are now being tested and being attempted. I think I just I fastly move away in my slide, but there was a very interesting idea about the serration. It's a sawtooth implementation in the leading edge and the trailing edge of the propeller blades, and people believe that it will significantly reduce the acoustic noise. So that's one of the examples people have been doing right now.
Okay, thanks. So Professor Seung-Jin Song from Seoul National University has a question. So he's asking, in addition to this scholastic output, what will be the final deliverables from your ERC in 7 years?
Well, my research center will focus on the software rather than the hardware. Even though we believe we will be able to demonstrate our capabilities of that software by flying, by testing the prototype vehicle, but the much of the effort will be focused on the software. Software is not an easy business, because in the field of rotorcraft, there are just few numbers of softwares which has been used and which has been certified by the people, by the research engineers, such as CANRA2 and the ANDARC. And those softwares are some of them are quite expensive commercial programs. The others are limited to the usage inside the United States. So my centers, the primary objective is to build comparable and capable software, which is mostly specialized in the rotorcraft and the UAM.
Okay, hope it answered Professor Song's question. If there's no further question from the audience, we can conclude the session number 1. So thank you everyone for attending. This concludes session 1, and now we'll take 15-minute break and proceed to session 2 in 15 minutes. Thank you again.
Thank you, Professor Kim.
Thank you, Professor Kim.
Thank you, everyone.
Everyone. Yeah.
네, 세션 2 시작하시면 되시겠습니다.
Okay. Good afternoon, everyone. My name is Yung-Gyo, the professor of material science and engineering at Seoul National University. I'll be your chair for session 2, the innovation for materials in aerospace industry. I'm looking forward to listen to the 3 variable talks from the 3 distinguished speakers from India and Korea to learn more about the materials in aerospace industry today. So let me introduce you the speakers for session 2. The first speaker is Professor Banerjee. I will briefly introduce Professor Banerjee. He graduated from Indian Institute of Technology in Madras and obtained PhD in metallurgy from Indian Institute of Science in Bangalore. Dr. Banerjee is studied the structure property relationship with titanium alloys, and then he also studied the intermetallic-based titanium alloy system for use in the high temperature application. As the director of Defense Metallurgical Research Laboratory, Dr. Banerjee provided leadership for many critical defense-related materials programs, and he also contributed to military engine and combat aircraft programs and other systems. Since 2010, he is one of the faculty. He is the faculty in Department of Material Science, Indian Institute of Science in Bangalore. Okay, Professor Banerjee, please start your presentation. Thank you.
Thank you very much. Let me share my screen. Yes. So good morning, everybody, and thank you very much for inviting me to this workshop. I was very happy to visit Korea at the second such workshop and enjoy your hospitality. And it is unfortunate that I could not be there this time as well. But thank you very much again. And today what I shall do is to briefly describe to you our materials manufacturing capability and our supporting research and development in India's aerospace sector. The space program is supported by is run by the Indian Space Research Organization. And fortunately, Mr. Somanath, Director of VSSC, will be talking later in this session, so I shall not talk about that. But I shall be talking primarily about military aircraft development and production. And this is in India, the subject matter for the Defense Research and Development Organization and the Hindustan Aeronautics Limited. And it's supported by a manufacturing company for specialty materials mill forms, Midhani, which is also under the Ministry of Defense. And so our programs encompass military aircraft development, airborne early warning system development, UAV development, missile development, as well as military gas turbine engine development. And in this talk, I'll focus essentially on aircraft and military gas turbine development. So for some reason, my slide is stuck. It's not moving. Okay. Okay, right, now it's moving. So these organizations are based primarily in the southern part of India, in these cities in the southern part of India. And they're all supported by significant private industry manufacturing, both at the subsystem and component level. But systems design is done essentially by our government organizations, such as HAL, DRDO, and the Indian Space Research Organization. We have made significant efforts to integrate the materials ecosystem, that is, integrate manufacturing technology and engineering to production, with the systems development environment, and with laboratory research in several areas. And so the Aeronautical Research and Development Board of India supports this integration through research programs which address structural materials, surface engineering, life extension science and technology, advanced manufacturing, computational modeling support, and sensors. Our flagship program of the Defense Research and Development Organization, NHAL, is our light aircraft, combat aircraft program. And this is also called the Tejas. This aircraft is called the Tejas. It has received full operational clearance from the Indian Air Force. And if you look at the materials distribution in this combat aircraft, it's essentially composed of about 40% of composite material. And so we have learned how to manufacture composites for such critical primary structures, the fuselage, the airframe, fuselage, wings, and so on. And both our manufacturing is both through conventional autoclave methods as well as vacuum assisted resin transfer molding processes, and including carbon fiber manufacturing. We
Professor
are
Banerjee,
yeah.
Sorry for
Yes.
interruption. Can you somehow we show the that the presentation display is?
I'm sorry.
Can you share the presentation?
Reshare again.
Yeah,
Again?
right now we are not showing the slideshow.
Oh, okay.
Yeah, thank you. Thank you very much.
You can see it now?
Yeah, you can have a slideshow.
Okay. Can you see it?
We are showing the slide in the next slide, and while you are sharing this presentation.
Yes. Are you seeing the slide on carbon fibers and composites now?
We are looking at the PowerPoint program, which is showing the current slide and as well as the next slide, and also the note.
Oh, I see. Okay. So what I will do, okay, I do not know how to change that.
No, Pankaj, earlier you have changed.
F5, use the slideshow left tab.
Full screen, full screen.
It is on full screen now. So maybe I will show it not in full screen, but I will show it in this mode. Is this okay?
Oh, okay. This is okay. Yeah,
I will use this so that you do not see both slides.
Yeah, thank you.
Okay, thank you. So I'm sorry about that. So we have developed in our country complete polymer matrix composite manufacturing capability, including autoclave manufacturing processes, vacuum-assisted resin transfer molding processes, as well as carbon fiber manufacturing. And at this time, we are trying to derive the benefits of such composites into new methods of varying the architecture of such composites to get a precise mechanical response in specific parts of the system. We are also trying to utilize the advantages of such composites by the embedding of smart sensors and actuators, which will allow parts to meet complex multifunctional requirements. An example of such a program is the use of sensors in integrated vehicle structural health monitoring. And so we have for you examples of such sensors, which are integrated into the fuselage and wing structures to show early crack detection or piezoelectric dynamic pressure sensors, which provide data on pressure on the aircraft airframes or even aero-engine structures, and also the possibility, if you detect cracks, of self-healing that allows the healing of such cracks in situ when they're formed. We have learned how to design with composites. So, for example, when such an aircraft undergoes combat, there is an extremely complex loading system that the composite fuselage and wing meets. So we have learned how to design with composites to handle these very complex loading efforts. And in designing, we have also have established capability to test full aircraft structures on the ground with loads that simulate the flight conditions in the material. Other critical materials that are used in the light combat aircraft are, for example, high-strength titanium alloys, which are used in such parts, and quite uniquely, shape memory couplings that couple these assemblies, these pipes for the transfer of pressurized fuel and air, which is a very important part of the hydraulic system of the aircraft. The aero engine environment is, of course, an extreme environment for materials. So revolutions greater than 10,000 RPM lead to fatigue. High temperatures lead to oxidation. Bird, sand, and ash ingestion at high velocities lead to various forms of impact damage, corrosion, and erosion. The key materials in such an aircraft are titanium in the front section of the aero engine, nickel-based alloys in the turbine, and perhaps ceramic matrix composites at the exhaust. The efficiency of the turbine, gas turbine, is of course determined by the Brayton cycle in its thermodynamics, and therefore the combustion temperature determines the thermodynamic efficiency of the engine. So these materials in the turbine section are extremely critical, and then high pressure ratios of the compressor drives the adiabatic heating that is important for combustion of the air with the fuel. The turbine materials are the most critical parts of the aero engine. And we have today manufacturing both research and manufacturing capability of single crystal nickel-based material, directionally solidified nickel-based alloys, equiax components, or such integrally cast structures. The entire process, starting from die design to core manufacture and injection, because these blades are hollow, and then ceramic molding and the casting processes have been developed in our laboratories and are under production also at the Hindustan Aeronautics Limited in production. We support this process capability, this manufacturing capability, by materials research of such superalloys. And I show you examples of atomistic mechanisms of materials deformation during creep of such materials. For example, the shear of the two-phase structure and the Ni3Al structure to form various kinds of faults. The analysis of those faults in terms of segregation to those faults by atom probe tomography techniques or by very high resolution electron microscopy techniques. And the understanding of these processes inform the alloy design efforts in our laboratories. The materials in the turbine are complex material systems. The turbine entry temperature in today's aero engines is actually much higher than the melting point of the nickel-based superalloy that is used as the material. And this is made possible by casting hollow blades, which allows internal cooling airflow through the blades. It is made possible by oxidation-resistant coatings on the blade's surface and above the oxidation-resistant coating, a thermally insulating ceramic coating. And therefore, this is actually a material system. And therefore, we have research supporting the understanding of the mechanics of such material systems. So small volume testing to understand the micromechanics of mechanical behavior at just the ceramic coatings, at the oxidation coatings, and in the substrates, and the ability to combine this micromechanical behavior at each portion of the structure into a whole material system response in response to the dynamics of the aero engine. Titanium occupies the front parts, the fan and the compressor stages of the engine. We have some of the largest titanium deposits in the world on the western coast of our country, and we have developed the technologies to extract titanium from these titanium ores at a production scale. And we have the capability at Midhani to transform titanium and its alloys into various components that are required in aero engines. Supporting this manufacturing capability is our research on modeling-based processing microstructure property linkages, which are extremely important to improve the efficiency and the yield of the manufacturing processes. So, for example, the complete die design, the materials response at different strain rates and temperatures, the flow of the material into dies, coupled with an understanding of strain rate, and temperature at different portions of the component, and the microstructural inhomogeneities that this distribution might lead to, and the assessment of the final component in relation to all these operations. And this is an example of micro holes in titanium alloys for cooling of some critical parts, designed by ultra-short duration pulse lasers. And the uniformity and the materials behavior around these micro holes are a part of research that we support through our Aeronautics Research and Development Board projects. The understanding of process capability is supported by the understanding of plasticity in these two-phase structures, microstructures that constitute titanium alloys. So the determination of local properties in such structures, the critical resolve shear stress of various phases through nanoindentation techniques combined with FEM analysis, crystal plasticity modeling to understand the strain development and strain partitioning in such structures, coupled with experimental understanding of strain partitioning. All of these together provide models to understand the mechanical behavior of such structures, for example, under fatigue loading. Carbon silicon carbide systems form a critical part of the end stages of the aero engine. And increasingly, efforts are being made to use silicon carbide composites in the turbine section to replace the cooled turbine blades, because the cooling process, extracting cooling air from the compressor, results in losses of efficiency in the engine. And therefore, we have made efforts in understanding the entire process of composite production and the supporting characterization of microstructure, of coatings for environmental resistance, the failure mechanisms of such materials in components such as this. And here is an example of a convergent divergent nozzle flap in our aero engines made with carbon silicon carbide. We also, in an entirely different effort, support the development of gallium nitride-based high-power, high-frequency devices, because these are important in various electronic devices, such as transmit-receive modules in radar systems. So we understand device performance in terms of the underlying materials science, which looks at the perfection of the atomic structure across the active layers, as well as the strain profiles and defect structures, and so on, to understand the performance of these devices. We are moving towards an integration of all this capability that I described to you by combining our capability in materials processing performance databases with advanced manufacturing techniques such as additive manufacturing, including topology optimization as well as gradient structures for improved functionality of such products. Supporting this manufacturing effort is initiatives supported by the Department of Heavy Industry of the Government of India towards Industry 4.0 capability. So, for example, we have centers of excellence in advanced manufacturing at IIT Kharagpur and the Indian Institute of Science, which aims to develop smart manufacturing capability in a consortium approach with industry partners. For example, at IISc, we are developing automation-intensive platforms, but also incorporating smart capability into legacy systems, which are labor-intensive platforms. So thank you very much. I will end here. I've tried to describe to you our capability in these programs and the supporting research and development effort into such programs and our efforts to integrate this total ecosystem. Thank you very much.
Yep. Thank you, Professor Bannerjee, for introducing the various programs operated in India. Let's now move to the next speaker. Dr. Young-Nam Kwon, Kwon Young-Nam, will deliver a speech. His title is The Status of Korea Aerospace Materials Industry. Do we really have to run domestic supply chain? Before he presents his research, I will briefly introduce him. He got MS undergraduate in Yonsei University, and he got PhD at postdoc, and he got postdoc at MIT, and he is working on KIMS, Korea Institute of Materials Science, as a researcher. He is engaged in aerospace materials development and characterization working over there. Okay, thank you.
Thank you, Chairman. My slide looks well.
Yep, it looks perfect. Thank you.
Thank you. Hello, my name is Young-Nam Kwon, working Aerospace Materials Center at KIMS. I understand that India is the forefront of aerospace industry, including space projectiles and missiles. I'm glad to have an opportunity to participate in this today's workshop and talk about common interests. What I'm going to present today is about the aerospace material industry status in Korea. Recently, the localization or self-reliant supply of aerospace materials has received a great attention in Korea. I'd like to talk about why this happened and what's going on next. So at first, I will briefly introduce my workplace, KIMS, and Aerospace Material Center. Then I go to aerospace material industries in Korea. Lastly, I will tell you about the project to develop, design allowable data of aerospace material started this year. Okay. Yeah, KIMS, Korea Institute of Material Science, is a government-funded research lab that is under the control of NIST, National Research Council of Science and Technology. And the main job is material R&D and testing, evaluation, and technical support Our research area is all over around metals, ceramics, powders, and composite materials, surface technologies, and the material processing. I belong to material processing department. Okay, we started from, this slide shows history of KIMS. We started as KTIMM. Actually, we had started from testings, actually. Last year, we started independent. We became independent institute in last November, actually. The English name is the same as in the past, but it has grown into Central Institute for Material Research in Korea. So we are in Changwon. KIM's headquarters is in Changwon, where I am now. Changwon is located in the southeastern part of Korean Peninsula. KAI, Hanwha Aerospace, and KAL, K-A-I-L, the major three companies in Korean aerospace industries are within 1 hour drive from here. So as of March of this year, our employees 663 and budgets are $110 million. So Aerospace Material Center, my center, has various machines for testing materials. Most testing is focused on the coupons and elements that require the statistical analysis. For aerospace materials, fatigue and dynamic properties are very important. We operate various hydraulic machines up to 1,200 kilonewtons. We have horizontal fatigue testers for environmental testing, thermomechanical machines for high temperature alloys, and we also have tension torsion testers. We also run high electromagnetic fatigue testers and ultrasonic fatigue testers for high frequency testings. In addition, we operate the residual stress measurement machines. With these machines, we generate and are producing material properties and element testing results for KFX program. KF is currently under development in Korea. So another job, our center is manufacturing technology for aerospace parts. Recent work on titanium part forming are shown in the slide. We have developed with collaborating companies over the past few years. We also have capability of superplastic forming and diffusion bonding for aerospace parts. Over the last 3 or 4 years, our center has focused on to develop a residual stress measurement and the predictions. Most frequently used manufacturing method for aerospace part is machining. With machining, we only utilize 10% or 20% of input material. Residual stress during material manufacturing processes, also as well as machining processes causing undesired deformations, so it fails. So we are actively developing technology to predict and control the residual stresses arising from material manufacturing steps, also machining processes. The final thing we are focused on is develop hydrogen fuel cell system for drones. For the purpose to prove the excellency of our fuel cell systems, we developed drones in this figure. We built that drone and flew more than 6 hours last year. For fuel cell for drones should be able to effectively respond to change in power demand during flight. We are trying to improve to fly more than 12 hours in next year. So from now on, I will talk about Korea's aerospace material industry. Well, the biggest difference between the other transport industries and aerospace industries is the level of safety issues. Airworthiness has detailed regulations ranging from aerospace materials to determine whether aircraft is suitable for safe flight. Korea actually followed the aerospace safety regulations of Western countries, mostly from the United States. Therefore, Russian or Chinese-built planes did not satisfy Korea's airworthiness regulation are not flying commercially to Korea. So strict airworthiness regulation related to history of aircraft structure development, as you can see on the slide. The introduction of linear fracture mechanics in aircraft design in the 70s required more accurate material property data, especially fatigue data, and has influenced the aerospace material development too. The property of aerospace material defined by Aerospace Safety Act are usually defined as design allowable. This example table shows allowable data for titanium 6-pole alloys in the MPDS handbook, which must be used from design stage to obtain airworthiness certifications to obtain design allowables for one material. A test metrics, as shown below here, requires a variety of tests with almost 1,800 specimens. Static tests such as tensile compression basically obtains statistically safe values by collecting specimens from 10 heat and the 10 lot material samples, which means melting and manufacturing 10 times to provide for testing. Even one material presents different material properties depending on material type, heat treatment condition, and thickness. It means, it takes quite a lot of effort and money to make this single design variable tables. I will briefly introduce you the history of Korean aerospace industry on this slide. In the 80s, the license assembled production began, such as F5, UH-16, F-16, an offset program led by Korean OEM to participation in civil aircraft part manufacturing business. Since 90s, independent development of many military aircraft has begun, such as KT-1 and T-15. The most representative achievement or supersonic trainer T-50 and the development of Hyoun, a transport helicopter. In the 2010 development of KF, Korean jet fighter is underway. So this slide shows the aircraft development developed by KARI, Korea Aerospace Industries. Most aircrafts are military. On April 9th of this year, there was KFX Aurora event. KFX fighter. Well, flight test is scheduled on next year. So, however, the size of Korean aerospace industry is very, very small, less than 1% of global production. I think the biggest reason is the incomplete supply chain. As you can see on the slide, basically there are no material suppliers in Korea. On the other hand, Korea's car makers, semiconductors, IT industry has very strong supply chains. Globally, assembly production capability has reached similar technical levels, but material component production techniques does not. Depending on the amount of purchase, aerospace material parts vary in price and delivery schedule, which will have significant impact on final competitiveness. Also, we experienced Japan's export regulations in semiconductors. So global supply chain can be very fragile and problematic. In particular, aerospace material, which are closely related to defense, are subject to major export regulations. Right now, the aerospace material production in Korea is limited to the production of 100 ton of aluminum extrusion. The first reason is lack of technology to manufacturing aerospace grade materials. The second may be more important. Domestic aerospace industry is very small. It is not attractive investment. Traditionally, materials industry is represented by high risk and high profit. Narrow domestic aerospace material market is preventing development of aerospace materials. But Japan is a good example of, I think we can learn from Japan. Japan can be a lesson for Korean aerospace material industries. Actually, based on strong material and manufacturing capability in Japan, they could create clustering structures involving material, parts, and OEM industries. So I will briefly tell you about the demand for aerospace materials in Korea. Actually, annual production of domestic aerospace material is very small. We need a lot of materials. However, the development of aerospace material through government support and civil development by private sector is underway. So the actually government plan to support the aerospace material industries in many ways. And in the private sector, voluntary development between material companies and OEMs is underway. KIMS is one of them, helping and supporting industries in many ways. And why do Korean government and private companies show great interest in developing aerospace materials? The first reason is Korea aerospace industry OEM companies want to increase RSP, sales volume. In addition, there are a significant move to reshape supply chain in aerospace industry. So Korean aerospace OEM companies eagerly want to make use of this situation. They seem to think that stable and cheap material supply is essential to make change. And number two driving force is Korean government. Actually, you can easily guess, I can easily guess what Korean government thinks by reading newspapers. Actually, Ministry of Trade, Industry and Energy announced industry development plan, and President advisor, science technology advisor for a direction for developing space industries recently. Actually, Korea declared a participation in NASA Artemis project. Okay, and but the last driving force, I think, is future mobile development, such as UAM. There's a big markets available in the future. So actually, UAM is aircraft. There are many startups, aerospace OEMs, automotive industries to design and build UAM, but according to current strict regulation, it is classified as aircraft, should meet airworthiness regulations. So the material used in the future mobile industry, mobility industry is expected to be, is huge. So that is, driving force to, to Korean, for Korean material industry are interested in the aerospace materials. In the last chapter, I will wrap up the presentation by explaining the recent started aerospace material design allowable value data development project. As told before, aerospace material must obtain material properties following the regulations. In this project, we develop design available design allowables for aluminums, titaniums, and fasteners, and nickels. So we are trying to develop 15 different type of materials data. So the strategies for selecting target materials are shown in this slide. Well, just look at it. So we have some roadmaps to apply the localized material in the future. This slide is about research interest in Korean aerospace research community. I mainly talk about the commercial, actually legacy materials such as aluminum, titanium, nickel alloys. However, new aircraft development requires new materials. But it must be very difficult for Korean material industry to achieve this, high quality standard, the price and the reliability required by aerospace industries. Actually, there are two businessmen in the picture, or such iconic figures. So they have flown on new wind. They just look, bring new wind in these space industries. Did they start with a perfect plan for Mars, or it just, has it come as a gradual development with constant challenges? I think it's a moment Korean researchers and businessmen with a sense of mission to go, go to Mars like, mind. I think this kind of mind are needed in Korean aerospace material industries. Okay. Thank you. I appreciate your kind attention. Thank you.
Yes. Thank you, Dr. Yung-Nam Kwon, for very interesting presentation and also very thoughtful presentation about the status of aerospace materials in Korea. Now it's time for invite the last speaker of the session. It's the Mr. Somanas. He is the director of Vikram Sarabhai Space Center, VSSC, of Indian Space Research Organization, ISRO, which is the lead central responsibility for the development of launch vehicles. In the 35 years of service in ISRO, Mr. Somanas is handling the various responsibilities, such as the director of the Liquid Population System Center and etc. He is the strong background of designing, development, and management of launch vehicle systems, and he is presently serving the chairman of the Management Council of the Launch Vehicle Programs and Human Space Flight Programs, and steering the technology development and management across the ISRO centers. He will talk about the materials development of the Indian space program. Okay, thank you.
Good afternoon, good morning. I hope I am audible. Okay.
Yeah, we can hear you well. Thank you.
Oh, thank you. Hope my slides are also visible.
Yeah, the slides are perfect. Thank you.
Okay. Thank you. I'll be talking on the materials development for Indian space program. We had interesting talk on the same topic by Professor Banerjee and also from Yung-Nam Kwon. So I will be covering the materials development route that we followed for the space program and our future outlook on this program. So that's what I thought of covering now. Before I start, I must tell the pioneers in Indian space program. Our program started by Dr. Vikram Sarabhai, taken a proper shape by Professor Satish Dhawan. But when it comes to material development, we must give the credit to Professor Brahm Prakash, who was the first director of Vikram Sarabhai Space Center, where I belong, who laid the foundation for material research and also the development and indigenization program, and also interfacing with the industries in India and making them the real partners in the development program, which already Dr. Dipankar Banerjee explained. With regard to the evolution of materials for space program, if you look back on the launch vehicle program we started in 80s, it was mostly on the procured materials that we built the first of rockets. Slowly, the program went into development of materials in India in 90s, with the steels and aluminum and titanium getting slowly indigenized, and also beginning of the superalloys for the cryogenic program getting initiated. Later, only very late in the 2000, only the alloys of aluminum started indigenizing. We started the production, again the titanium sponge plant and high temperature material development. Later in 2010, the specific elements meant for this were developed. And today we are looking at some specific development, also more of industrialization. The structural materials are well known in rockets. Some of them are in the aluminum, then titanium, composites, and mixed combination of them makes the structures of the rocket, in addition to the steels that goes into the solid motors and pressure vessels of that rocket. Aluminum, primarily we use 2219 as aluminum, which is a weldable alloy for the manufacturing of the propellant tanks, and also titanium for some of the propellant tanks and pressure vessels in the rocket. And composites are well used in the where light mass is very important for the upper stages, especially the fairings, the payload compartments, as well as the equipment decks, which goes into the rocket. The materials for spacecraft propulsion, they vary in the form of mostly the titanium varieties goes into the propulsion tanks and related components of the propulsion, and high temperature materials like columbium, C103 for making the high temperature engines, and various steels for the elements that goes for the propulsion systems of the rocket, of the spacecraft. Similarly, there are materials for cryogenic and semi-cryogenic engines. The engines are a very complex assembly, typically something like 50 to 80 types of alloys that makes an engine. And we started by procurement early part of the program, but later many of these alloys slowly got indigenized by the support of the industries that Professor Banerjee mentioned. But still, there are many still being imported, but they are small quantities, quantity requirement, which doesn't substantiate the development effort in terms of large volume production. Some of them very important one are the copper, which we have realized for the thrust chamber where the high conductivities are required. And it's not only the alloys that has been indigenized, but also the manufacturing process into different shapes and forms that suits the engine manufacturing requirements. Then I speak very briefly on the metallic materials and their current status. If you look at the very key building blocks of the rocket motors, the solid boosters are the 15C-6 and marine steel M250. Both were, though 15C is not an Indian alloy, but then it was indigenized in Indian industries, and we have now the full end-to-end production capability, including the forgings, which have been realized through the Indian forging industry. And marine steel development, M250 development is something very, very remarkable, in which the very large amount of work which was done early time in characterizing the material and also establishing the various processes at Midani, Rourkela steel plant, and various other supporting industries for characterizing this material way back in 80s. But that fed to the development of the PSLV rocket boosters at a later point of time, and now they are the building blocks of our solid motor, the heritage. And currently, we are looking at even changing that alloy to a modified ESR modified 15C-6, where we are looking at flow forming these segments because the cost associated with the alloying elements in the marine steel is something very prohibitive, and we were very successful in indigenizing this ESR modified 15C-6 and also making the billets for the rings as preforms and also flow forming them very successfully in an external facility. Where the criticality in this type of segments where the heat treatment activity, and that also has been very effectively carried out, and hardwares have been produced. Various facilities were established in industry, and these were not done within the space institutions, but it is done in industries such as the plate rolling facilities, the melting facilities, the ring rolling facilities were all established across various industries. Now these facilities are supporting various alloys and their production for meeting quality, aerospace quality requirements such as the fracture toughness evaluation, development of the filler wires and welding aspects, or even the quality which is required for the aerospace applications, such as the specific ultrasonic quality requirements for these alloys are met by these established facilities now. The aluminum alloy indigenization was a very late program, but then it is now feeding benefits in terms of the ability to melt all those alloys, convert them into various forms like the slabs in one industry, sheet rolling yet another industries, rolling of these rings in another industry, converting them into forgings, rods and blocks and pipes in yet another industry. See, this industrial cluster currently supports all the requirements of these alloys for our program. Similarly, the processing facilities were also established in various industries, including the heat treatment furnaces, the plate rolling mills, and also the billets up to 900 millimeters have been realized for meeting the large forging requirements for our big diameter boosters. Titanium is another important element for the space program, started with the TA6AL4V, the workhorse material for gas bottles and propellant tanks. And later they were developed in labs, but then the development of large-scale titanium started in Mithani, has already been mentioned, and we had we have production of titanium sponge started once we established the plant using the ores available through the technologies available here, and later the sponge conversion to the alloy and also the required forms, and realizing the products started a few years back. Now they have been inducted into the program of all the launch vehicles and systems in a big way. Another important requirement was the indigenization of the various elements that goes to the high temperature materials, such as the columbium, the KC20WN, through the production of the hafnium and niobium production in the plants that have been established in some of these labs of the CMET and NFCs, which are situated at Hyderabad city in India. One of the important requirement of cryogenic engines and even the restorable engines were the castings, mostly the investment castings, and specifically for the cryogenic and semi-cryogenic engines, the casting requirements are mostly of the titanium superalloys as well as the aluminum based alloys were successfully realized through various routes, including the melting, casting technologies, and also establishing proper quality of these forgings have been established over the years. That has been a very important input for realizing the engines within India itself. Today, we are looking at manufacturing these castings through additive manufacturing routes. Of course, in the later presentations, maybe today we will be discussing some of these accomplishments. Now, looking at the materials which are very important for rocket program, the high temperature materials. Our foray into the high temperature material development started when we tested the space capsule recovery experiment way back in 2007, but the development program of various tiles like the silica tiles, flexible insulation system, code bricks, and silica aerogel, all this started over the years, and they have been injected into this program very successfully, where we did the orbital recovery experiment. And later these elements were inducted into the reusable launch vehicle technology demonstration, which was launched in 2016. And over the years, we are trying to expand this capability to feed to the two-stage to orbit reusable launch vehicles. So the various elements which goes to the development of high temperature material, including the USTCs, will be described in the following slides. Coming to the high temperature materials, the future requirements are in the where the application temperature goes much higher than 1600, where there is a material limit coming to, and how to create materials which can withstand up to 2400, which is already be there working around the globe through the USTC is one of the focus leading research activity where some of these materials can feed to creating hypersonic vehicles, the elements into the thermal protection systems, and also nozzle inserts which will go into the rocket. We are now currently looking at manufacturing of some of these elements for our reusable launch vehicle, where the nose caps, the wing leading edges have been realized through various carbon form routes, but then sintering as well as the formation of these materials are currently going on within the facilities in ISRO. The high temperature materials requirements are really demanding for vehicles like this, where we are looking at the hypersonic the scramjet-based propulsion system for developing vehicles of this nature, where the high temperature elements are very important for the combustion chambers and as well as the external aerodynamic systems. For example, if you look at the scramjet powered hypersonic vehicle, the air intake ramps typically the 1400 degree. The combustor divergent region temperature goes up to 2200 degrees Celsius, where the carbon silicon carbide USTC coatings becomes very essential. Similarly, this technology once developed will feed into various other elements of the rocket systems, such as the re-entry vehicles, the nozzle throat inserts, and various the elements that goes into the building blocks of the rocket. Similarly, the high temperature materials and the regular alloys, but there are special materials which are, I'm not talking about everything, but that is being done, but only as typical of alloys which are required to meeting specific demands. For example, tuning forks materials that goes into the gyros, where the very narrow range of properties for resonating vibrating systems, where symmetry of the modes becomes very important. Another development is nitrogen alloyed martensitic stainless steels with carbide dispersion are developed for cryogenic applications. The titanium 2.5 SN ELI grade alloys for control of hydrogen required for the cryogenic applications for helium storage. So these were some of the typical alloys which have been developed after great effort. Another important development was copper alloys for liquid engines, where the forming of this copper is very, very critical, and also under different cycles of temperature, the accumulated plastic strains had to be limited. So these copper plates were formed and alloyed and formed on some of the Indian facilities, and they have been successfully used in the cryogenic engine program, where the thrust chambers with narrow chemically milled cavities and brazing has been successfully used with stainless steel for manufacturing of these engines. So similarly, for this engine manufacturing, another group of alloys that were developed is for brazing technology for copper to stainless steel and various other elemental bracings for making injector heads, the thrust preburner elements, and maybe some of the alloys for brazing covar to alumina for making traveling wave tubes, amplifiers for spacecraft applications. In addition to the metallic materials, there are so many chemical materials that are required for space program, which includes thermal protection systems, which are silica phenolic, ablative systems, carbon disperse systems, dielectric materials, nylons, which are required for various applications. So there is a huge list of materials that are being developed to meet the space program, meeting those quality requirements. Some specific materials that are very important, shape memory alloys, which goes to manufacturing the unfurlable antenna, actuators for spacecrafts, and then yet another the super invar alloy, which is going into a low coefficient of thermal expansion alloys required for mounting optical systems in spacecraft. They have been successfully developed through the technologies available in ISRO and industry. A group of people are working on electronic ceramics, and these are very, very important for high frequency applications where the RF systems are used. We look at the high Q materials for KU band satellite multiplexers, dielectric ceramics for antenna and resonators, and various elements of RF systems, and ceramic green tapes have been successfully developed using the industry interfacing and the technology available in ISRO. Now looking at the research into the future, various new material developments are there. They are into various groups for additive manufacturing materials, nanomaterials, and composites. Our focus is more on the high temperature materials, coatings, functionally graded materials, and electronic materials. Looking at the thermostructural domain, as I mentioned earlier, the thrust is in converting them into ceramic matrix composite, which are near net shaped so that machining can be simplified, and also high temperature dense sintered product with the zirconium diboroid and hafnium diboroid based CMCs, and also carbon composites with the multi-dimensional capability. In the thermostructural area, again, for a cryogenic engine, currently the material temperature limits are only up to 500 degrees centigrade, and we would like to increase it to something like 800 using these alloys development. Similarly, for titanium alloys, beta titanium alloy development for gas bottles, which can bring in significant weight saving and also high processability for these alloys for tank manufacturing. In the thermal protection domain, of course, there are so much of development which is required to be undertaken, and currently the research is going on manufacturing the silica tiles in larger size, metallic thermal protection systems, ODS-based metallic TPS materials, and forming thin foils and sheets for manufacturing metallic TPS materials, carbon foams that can be used for high temperature applications with the ablative capability. In the nano and smart and functionally graded materials, also the research work and the developments are in the area of smart materials, the smart material fluids, MR fluids, and also functionally graded materials production. Now, we have quite a large number of thrust areas have been identified. Some of the additional area, which includes development of a titanium alloy, which will work up to high temperature area with the creep resistant alloys, development of high entropy alloys with and also use of extensive simulation tools, which is some of the very key area in the current domain. In the electric propulsion system, there are many new materials which are required to be developed, including thermonic emitter materials and also silicon germanium alloy for thermoelectric devices. Band gap material are required to be developed for high gigahertz, terahertz applications. And also electromagnetic materials for high temperature, high power dielectric materials are also identified as a very key element for the recent developments. And also looking at the high hydrophobic flexible silica aerogel composites for various usages in the thermal protection system, internal and external to the rockets. And also high temperature ceramics and coating processes are very, very important to be developed in the near term. So in summarizing the most important material development I have summarized, but what we see here is the industry production, and in a cost-effective manner, is something that has not been achieved because the demand for these materials are small, and operation of the industries to break even is not really achieved. So this is one goal that we have set to industrialize the production and achieve the cost-effective manufacturing, and also operation of these facilities by industries through the established space qualified process for consistent production, and also enabling industries to do R&D in materials development. And currently that is being done within the organization. And in my talk, I have really identified some of those key area and domains. I believe that the thrust that we are giving to the industries to take on this will really benefit in expanding the space program substantially in the coming years. Thank you. Thank you so much.
Thank you. Thanks for all speakers to have a very nice presentation and very good overview of what's going on in aerospace materials area. Let's move to now the session is open for the question and answers. We now you can ask questions directly to the speaker, and also we received the questions from YouTube. We also asked the speakers to turn on the camera. While we are receiving the questions, I will ask some questions. First, Professor Banaraj, I wonder that you're talking about the three major areas of the turbine development for the nickel-based superalloy and titanium and silicon carbide, carbon silicon carbide system. Do you think that what is the most challengeable area among these three?
Today, for us in India, the carbon silicon carbide and the silicon carbide technology is the most challenging in India. I think in India, we have achieved a production maturity with titanium and nickel-based superalloys. with some exceptions. I'll talk about them, but certainly, and also to some extent, we are okay with carbon silicon carbide, that is carbon fiber and silicon carbide matrix. The development of silicon carbide fiber is a key challenge that we are attempting now. And of course, the reason for looking at silicon carbide instead of carbon silicon carbide is in long-term applications in the aero engine, specifically in the turbine parts, where if you can use such components without cooling, it adds to the efficiency of the engine. So both silicon carbide fiber as well as the development of coatings for environmental resistance, including what is called CMAS, that is ash ingestion, are critical challenges for us right now. In the area of nickel-based superalloys, we are making serious efforts to develop powder metallurgy-based nickel-based superalloy disc material, aero engine turbine disc material. Today, we have capability to produce conventionally processed turbine disc material out of nickel-based superalloys. But in order to achieve higher temperatures, we need the powder metallurgy-based aero engine disc material.
Actually, I have a question to Dr. Banaj. Do you have your India own jet engine or jet engine commercially available?
We do not have our own jet engine. We have been trying to develop a military jet engine for a very long time, but we have not achieved the level of success that is required to put such an engine into actual operation. So all our aircraft, including the Tejas, the light combat aircraft, are running on either, sometimes American engines, sometimes British engines, and sometimes Russian engines.
So do you have plan to build or develop your own jet engines for?
Yes, that effort is continuing.
Okay, thanks a lot.
Thank you.
You are muted.
You are muted, Chairman.
It's a question to Mr. Sumanas. I'm very impressed that you are developing the aerospace launch systems and developing so many materials with this system. The India's strategy for developing such a aerospace launch system, you usually provide all the materials in domestic supply, like produced in India, or you also rely a global chain to supply some parts or some materials?
Of course, we have most of the materials in India, but we need to procure some materials from outside. For example, I will tell you in aluminum, if you look at, if you got a very, very thin sheets, there is a limitation of processing required. Of course, thicker sheets are well processed for most of the alloys, but when it comes to very thin sheets, which required for manufacturing lightweight structures, there is a limitation. Similarly, that we also are importing specific alloys that goes into some of the brazing items, some of the piping and tubing, etc. But if generally we look at the steels and aluminum, we have most of the alloys, and even titanium, we have most of the titanium requirement. But if you look at steels, the alloying elements for steels do come from outside, but they are not sufficient alloying elements, especially the especially the one which meant for the maraging steel, are procured from outside. So it is not 100% the Indian sourced alloys, but of course there is a dependency still.
You also mentioned that you are developing the various structural materials, but also some functional materials used in the aerospace, like the dielectrics and.
Oh yes, yes. They are done within India. We have a tie-up with industries who are capable of manufacturing those dielectric materials, and also we have laboratories internally who can produce them in small quantities and also do the research for dielectric materials.
May I also respond here? We really have the same problem that Dr. KWON mentioned in terms of the demand and building an industry to meet low demand. And therefore, very often the capital investment required to make large-scale, sophisticated, that capital investment is not often justified by the demand that exists in the country. Yes, so it's a balance that we try to achieve. Yes.
Yeah, it's all important issues in the aerospace industry material supplies. So
but of course, that is a good area for Korea-India collaboration. If one can identify larger markets in the two countries, and this is something I leave to Professor Manna and the president of the Korean Academy of Engineering to think about. Yes.
Yeah, exactly. Actually, this is the purpose of our workshop for finding out what's the area we can collaborate between the India and Korea. So I will ask all speakers to think about what area you are thinking is a good area we start with. So let's start Dr. Yung-Nam Kwon first, and then I'll ask you two of the Indian speakers to talk about your opinions.
Actually, well, I have gone through most of many of your materials you have shown today. Actually, I have experience to develop stainless steels for aircraft and titanium. I'm developing better titanium alloys for high toughness. These days, very thick forgings, which is 10 inches. And I am testing nickel alloys for high temperature applications. Also, actually, I have collaborated with thermal barrier coatings for rocket engine nodules. So I think most of topics you are working on are our works done in Korea, actually. And we are short of wide panels, thin aluminum rolling sheet and the plate, actually. So I think if it is really true, well, the UAM and the urban air mobility come true in coming future. So we need a large amount of aerospace grade materials. So, well, we have to prepare to supply those materials in coming years, okay? So I think, well, it doesn't matter which material we can collaborate it on first, aluminum, titanium, nickels, or coppers. So, and even composite materials. I do not work on the composite materials, but we will work on the structural composite materials. We are working on stealth material, actually, stealth composite materials. So I think, well, there are many chances. There are many candidates for collaborating. Okay.
Okay, thank you. and maybe in the Indian side?
Let me say some of the important demand of the new development from our side is in the high temperature materials, especially the abilities. For example, we were trying to develop an insulation system for our human capsule, where the density we have to clamp at around 0.5, but the heat of ablation and the thickness which were required to be accomplished, we are unable to do, and we are continuously doing R&D on it. So this is one core area where a re-entry heating handling through an ablation process. We try to work out with the carbon, then we try to work out with silica, various forms, but then it ultimately ends up with higher densities or higher thicknesses. So this is one area of research that currently we are working, especially when you work on with a porous structure, we find that the conductivity is actually increasing due to the internal radiation happening within the pores. So to that extent, the R&D on this had to be done. So this is one important area. Another important area is with regard to metallic thermal protection system, where we want to work with very thin steels, where we can construct the structure and the thermal protection together and use that as the structural thermal protection material for our airframes to handle the high temperature re-entry situation. So this is another important area. As we have mentioned earlier, as Professor Banerjee also mentioned, the manufacturing of aluminum is really, really huge in India. But most of the aluminum manufacturing is in commercial domain. It's not into the aerospace domain yet. Because they are reluctant to work on aerospace domain, because the intake by the rocket industry or aircraft industry for use is very, very small compared to their capability to produce huge quantity. So to create even a rolling station with the required cleanliness and also the required process control is too costly for them for that purpose. So this is yet another domain we are working, but then it is important that we have these materials either sourced from industries who have an ability to produce. Of course, it is coming from Europe and US today. Of course, this area is something that we can look to South Korea, where we have not explored your ability for this domain. Of course, this is something that we are looking at. And similarly, in titaniums also, they have huge amount of process capability. I believe here a lot of research is really needed. And lastly, of course, it will be discussed in the coming days on additive manufacturing. I think additive manufacturing, powder manufacturing is one topic we would like to look at in a big way in the coming years.
Okay. We were looking for the tomorrow's session about additive manufacturing.
Yeah.
Okay, thank you. Professor Banarag, is there anything you want to add?
I wish to add again in relation to Dr. Kwon's talk. It is very interesting. I mentioned, and Mr. Somana also mentioned, Midhani, the company which produces specialty alloy mill forms to aerospace standards. When this company was first started, it had no demand at all because there was no aeronautic, and it ran at a loss for almost 10 to 15 years. And then slowly the demand picked up, and now the company is doing very well. So sometimes it is necessary for government support to continue in a company till the demand picks up. But Midhani is very qualified to produce aeronautical and aerospace grade materials with very good quality control processes. And therefore, if Korea is beginning to invest in its own internal manufacturing, perhaps there is a good forum for industry collaboration in that area to develop the best practices on both sides. That is one aspect for metals and alloys. The other area I have mentioned in all the past conferences that we have had is that we are very interested in silicon carbide fiber development. And that is an area that, and environmental resistant coatings. And that is an area for R&D that I think would be most interesting. Thank you.
Okay. Thank you. Thanks for the all three speakers to very good, very interesting presentation as well as the discussion. Looks like we don't have any more questions from the audience. So it's now time to close the session too. I will appreciate the speakers and also audience who made today's workshop productive, even if we cannot meet face to face. But I hope soon in the near future, we meet again face to face and working together to development for aerospace physical materials. The workshop will be begin tomorrow as well, and tomorrow's topic will be the additive manufacturing for aerospace industry. I think that there will be also interesting talks in tomorrow as well. So let's see you all in tomorrow. And thanks again for today's workshop. Thank you very much.
Thank you.
Thank you very much.
Thank you. Tomorrow's topic will be the additive manufacturing for aerospace industry. I think that there will be also interesting talks in tomorrow as well.
Thank you for 잠시만요. All the speakers and chairs. Thank you very much for coming to the workshop day one. And I will send you email with some materials to follow up next step for wrap up this workshop. Thank you very much today.
Thank you.
Thank you very much.